An object at rest will remain at rest, and an object in motion will remain in motion with the same speed and in the same direction unless acted upon by an unbalanced external force. Newton's first law of motion is also known as the law of inertia. The concept of inertia was introduced before Newton by Galileo and Descartes, but Newton refined and expanded it. The law states that objects will not change their state of motion, either at rest or in uniform motion, unless a force is applied. This force must be unbalanced, meaning there is a net force acting on the object. If the forces acting on an object are balanced, the object will either remain stationary or continue moving at a constant velocity. The key concept in this law is inertia, which is the tendency of objects to resist changes in their motion. Every object has a natural state of motion, and it is only external forces that can alter this state. Inertia is directly related to mass. Objects with more mass have greater inertia, meaning they require more force to change their motion. If an object is at rest and no external force is acting on it, it will stay at rest. Similarly, if an object is moving with a constant speed in a straight line, it will continue to do so unless acted upon by a force. This explains why you can float in space, far from any gravitational forces. Without forces acting on you, you would continue moving indefinitely. When you are sitting in a car that suddenly stops, your body tends to lurch forward. This is because your body was in motion with the car. And when the car stopped, your body still wanted to continue moving in the same direction due to inertia. The concept of inertia helps us understand why seatbelts are important. They provide an external force to change the motion of your body when the car stops abruptly, preventing injury. This law also explains the motion of celestial bodies. The planets in the solar system continue in their orbits around the Sun due to their inertia unless influenced by gravitational forces. The acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to the object's mass. Newton's second law describes how the velocity of an object changes when it is subjected to an external force. The law highlights two key relationships. If the force applied to an object increases, the object's acceleration increases as well, assuming the mass remains constant. The more massive an object is, the less it will accelerate for the same amount of force applied. This law shows that the acceleration of an object depends on both the force applied and the object's mass. In essence, for the same force, a more massive object will accelerate less than a less massive object. If you apply the same force to a car and a bicycle, the bicycle will accelerate more because it has less mass than the car. The car, having more mass, will accelerate less for the same force. The rocket's engines generate a significant amount of force to overcome its weight. Initially, the rocket's mass is large because of the fuel, but as the fuel burns, the rocket's mass decreases, allowing it to accelerate faster, even with the same thrust. The second law is crucial for understanding how forces affect the motion of objects. It is particularly useful in engineering and physics to calculate the forces needed to move objects at desired accelerations. It also explains why heavier objects are harder to move. For example, a heavy truck requires more force to accelerate than a lighter car. For every action, there is an equal and opposite reaction. Newton's third law of motion deals with interactions between two objects. It states that whenever one object exerts a force on another, the second object exerts an equal but opposite force on the first object. These forces are equal in magnitude and opposite in direction, but act on different objects. This law explains why forces always occur in pairs. For example, if you push against a wall, the wall pushes back on you with an equal and opposite force. The force you exert on the wall is the action, and the force the wall exerts on you is the reaction. When you walk, your foot pushes back on the ground with a certain force, action, and the ground pushes forward on your foot with an equal and opposite force, reaction, propelling you forward. A rocket expels gas downwards, action, and in response, the rocket moves upwards, reaction. The expelled gas creates an opposite force that pushes the rocket in the other direction. The third law helps us understand the principle behind jet engines and rockets. The action of expelling gas downward creates the reaction that propels the rocket or jet forward. It is also important in understanding motion in all kinds of physical interactions, from simple contact forces like friction to complex systems like fluid dynamics. When applied together, Newton's three laws of motion provide a complete description of how objects move in response to forces. These laws explain everything from the motion of everyday objects to the complex interactions between celestial bodies. Inertia explains that objects continue in their current state of motion unless acted upon by an unbalanced force. Force and acceleration tells us how the motion of an object will change when a force is applied, and how the object's mass influences that change. Action and reaction describes the mutual forces that two interacting objects exert on each other, always in equal and opposite directions. These laws, though simple in principle, have wide-ranging applications and form the basis for much of classical mechanics, helping engineers, scientists, and everyday people understand and predict how objects will behave in various situations. Newton's laws are used extensively in the design and analysis of structures, vehicles, and machines. For example, the principles of motion are applied in vehicle safety systems, and the design of bridges and buildings to ensure they can withstand forces like wind, gravity, and seismic activity. The laws of motion are crucial for calculating trajectories, orbits, and launch dynamics of spacecraft. The motion of satellites, planets, and other celestial bodies can be predicted using Newton's laws. In sports, understanding motion helps in improving performance. For example, a sprinter's acceleration depends on the force they exert against the ground, and a soccer player's kick is an example of action and reaction at play. Newton's three laws of motion are foundational to our understanding of how objects move and interact. They provide clear explanations for the behavior of everything from everyday objects to complex systems in space. Whether applied in physics, engineering, or even sports, these laws remain essential tools for analyzing and predicting motion. They form the bedrock of classical mechanics, shaping much of the technology and understanding that drives modern science. In the context of modern physics, while Newton's laws are still widely used in many situations, they are refined and expanded upon by more advanced theories, such as Einstein's theory of relativity and quantum mechanics. Nonetheless, Newton's contributions remain an essential part of our scientific heritage, providing us with a framework that is still used to solve countless real-world problems today.